So apply electricity, the basic equation that we are doing is V is equal to I for now. That's the one I'm maintaining. And we've seen that some of the quantities are sinusoidal V or as the name I, right? Okay. And then we've seen that when we're writing these sinusoidal quantities, we don't draw them, the graphs always as a function of time, but at times we use phases, right? And we said the general way of representing these phases is that, so if it's let's say V, right, because they are AC, so V, small v, we have the peak quantity, right, because, and the sign, right, they are talking about sine waves, the most commonest, and then we have the value here, positive integer, right, and then we have the angular frequency, we have time, and we have plus or minus, and we have a phase angle, right. This is a basic way of writing, the general way of writing this sinusoidal quantities, right. But then there are other ways of writing them, especially when we want to do circuit analysis. Is much, this one here is a bit not clear, right, because you don't need all the features when we are doing the computations, the other features that we need, right. But then we've seen that if you have a phase of this sort, let's say if there's a VM or something, right, with respect to the coordinate system, right, it have some sort of x component, it have some sort of y component, it could even be here, right, and then y component to be here, it could be, so it has a s component, it has a y component, and then the angle that it makes with respect to the x-axis, positive x-axis, is this what we call theta here, right? So this one here is like kind of like positive theta, but if it were to be here, it would have been something like a negative theta, meaning this is lagging, this is leading. So negative is lag, positive is lead, right? Okay. So then now we're going to look at other ways of representing them, right? So the one we've seen at the top here is a way of representing these sinusoidal quantities or writing the phases as a function of time, right? But then we are going to look at another way. The other way we look at is what we call the rectangular form. Rectangular. And then when we hear of it, think of Cartesian, right? So, or Cartesian. Cartesian form, right? All right. And then we have another one. So this is one form. This is another. And then we have a third one, which is called a polar form, right? Polar form. We are going to look at each and every one of them easily. But before we go, let's look at the very first one, this one right here. You could clearly see that if you are trying to define a phasor, right, or a sinusoidal quantity, the parts that are very important to use when describing it is you basically end up using at least two, right? So you need, so this particular form here, we need VM, right, and then we need a phase angle, right. And we know that if you have this one right here, the peak, and then you have the phase angle, you can find some x components, which we've done, or you can find some y components, right. All right, so that's very clear. So you need at least at least at least at least two aspects of it. Two aspects, I'm going to put that in quotes. Two aspects needed to describe a phasor. Okay, so now we know that. So now we're going to look at the rectangular component, or the Cartesian component that we spoke of. So when you hear of this Cartesian, you know we have some kind of plane, like a 2D plane, XY, right? So now we're going to go over that. Okay, so now you're dealing with the Cartesian. All right. Okay, so what this one is saying is that it just helps you to find this component and y component, and the general way of representing this very one here. A minute, this could be current or voltage. So if it were to be current, you've done this, would have been something. Let's see, could be something like this. So I, and then we have Im, of course, it's sinusoidal, sine this, any positive integer, angular frequency, time, plus or minus phase angle, right? So it's just the same thing. Just for us to understand. So we can use any of them at any time. Okay. So now we are talking about the rectangular form or the Cartesian form, right? All right. So with view of this Cartesian plane, right? So something like this. Yeah. So what this one says is that for any phasor, we can represent them using so let's see if it's V, right? Let's use I now. So if it's current, right? another sinusoidal quantity current. One way that we can represent this is by using its S component, right, plus or minus, right, and then we have some complex operator, and then we have the Y component, right. So looking at this one very clearly, you get to see that we're actually using two features of the phasor just represented. So here we are using the S component of it, we are using the Y component of it. This J here is just a what do you call it, an operator. It could be that's constant. So at times you could actually see this J. There's no way you see it as J. So this J here in some references you see it as I, and we know this is equal to square root of -1, right? Okay, square root of -1. So that's what we are using here. So this is what the Cartesian or the rectangular form is saying, that you can represent the sinusoidal quantity this way. Then again, this can be voltage, just so we understand. So we have a V, right? And we have V S components plus or minus. We have a T, which is constant, and we have a V Y component, right? So that's what this one is saying. So clearly you can see that here again we are using just two components to describe the phasor, right? S component, Y component. And with this you can even go back to, you can turn it back to the, what's the name, this one, which is as a function of time, the very first one, right? So clearly you see that for the very first one, you see we have the peak if it's voltage, right? If it is voltage, we have the V is equal to Vm, we have sine, right? And then we have an integer, we have angular frequency plus or minus the phase angle, right? So if you want to get this Vm, you clearly know that you need this Vm here will be equal to the square root of Vx squared plus Vy squared, right? And that's what will give you the Vx, sorry, the Vm. And if you want to find this phase angle here, is basically the tan inverse of the Vy, whether positive or negative, right? And then plus or minus Vx, and that gives you the theta or the phase angle, right? So clearly we can see that the Cartesian system, the Cartesian or the rectangular form, can also be turned back to the original, the first one that we wrote, which is as a function of time, right? Yeah. The next form that we have is the polar, right? So it's also the same thing. What did we say when we are trying to represent the phasor? Basically, we need two components to make it complete, right? And now we've seen that when it comes to this one that we have here, we need the peak, right? We need the peak, and then we need the phase angle. And for the rectangular form, we've seen that if you want to do that one, you need the S component and you need the Y component of that quantity, right? Whether current or voltage, or right? But when it comes to the polar form, what you need is that you need a peak, right? You need a peak, right? Whether voltage or current, you need a peak, and you need a phase. So the rare one that is easier to get. So what this says is that if you're having this sinusoidal way, if you want to change the polar form, it's very straightforward. Just look at the values then write it straightforward, right? So that's this. So what this one says is that if you have, so the polar form, right? That was the polar form now. Okay. So the sinusoidal function that we have, which is Vm, which is, let's see, V. This is the third one, right? So if you have, let's say, V is equal to Vm, right, sine, and then you have this integer angular frequency time plus or minus phase angle, right? If you are changing the polar form, very straightforward. You just bring this peak value here, so something like Vm, and usually put it this way to show that it's a vector, right? And then we do this, and then we bring the phase angle here. So that's it. That's the way of writing the polar form. And clearly you can see that this one here to uses to the peak value and the phase angle. So whenever you're trying to represent a phasor, it's very clear that you need two, at least two, right? So the main ones are that you have you can either use the peak and the phase angle, or you have the S component and the Y component, right? Yeah, that's it. Example, we're going to see how we are going to write this particular one, the values we had from example 2, and in the additional phases, see how we write them in the Cartesian or the rectangular form and the polar form, right? So we know that when we're writing, we're doing it in the rectangular or the Cartesian form. All that we need is that we need an S component, right? If it's current, we need an S component. And then we need something like a J or times I, and then we need a Y component, right? And in this case, it's current, right? So just I is fine. So it could this, it could be this, or this, right? So the J, so it could be this, I, Y. Or times, it could even be this way. You have the Y component, right? And you have the G or the I here, right? But this is not common, right? So now we're going to do, looking at, so we're going to start with this part first. So looking at that part, it's very clear that we can get the X and Y component from it easily, right? Right. Okay, so let's do this. So this is just a verification work just to see how we can use them. But we are going to solve an example in that very particular one. Okay. So now we have this. We are working on this one here. Just the part. Okay. So we have to get the S component for that very part. Let's visualize this way. This means that if you are trying to write the I4 in a Cartesian or rectangular form, that's how to be done. So I4, right? I4. This is just one part of I4, and that's how to be. So we are trying to get the S component. So we know that the S, we are very much aware that this S component is equal to just the peak, right? And then we have a cos, and then we have the phase shift, right? And then the Y component is equal to the peak, sine, and then the phase angle, right? So that's very straightforward. So if we're trying to get the S component, we have the peak, which is 19 points minutes. Okay, so that's 19.9487, and always work in the number of decimal places as stated. Right? So we have cos, right? Then again, let's pay attention to the sign of the phase angle, right? So we're using to do something. So let's see. We know cos definitely cos, but whether it's leading or lagging, it'll still be on the positive x-axis, right? So cos, that's 10.62, right? So that's what gives us. So we have that. So that's the S component for just the first part. And that's, let's do 4dp, 19.6070, right? And then the Y component, right? So then let's pay attention to this. You see that it's lagging. So if you have to draw the phasor, let's see, x-axis Cartesian, right? So Cartesian plane, like this, like that, and we are seeing that it's lagging. So if it's lagging and it's here, meaning that the Y component should be negative, right? So that will mean that if you are writing it in this way, here will be negative, right? So it's negative. So we have a negative here. Okay. So we have a negative. Okay, negative. And then because you're looking for the Y component, we do what? Sine. Right, sine. Yeah, and that gives us the minus that's there. So that's minus. We have the minus already, right? So because we placed it in this one, so that's why I have it there. So minus 3 points. That's 4 dp, right? So let's see. We always add J. So we bring out J. Let's make it in below, right? J, and then we have 3.675 6, 4. Right, so that's just one part. Now move on to the next part, which has a different frequency. But one thing about these ones is that you're not clearly be able to, you will not be able to identify the frequency clearly from them. So you must pay attention and then not add them straight forward, else you're writing a different thing. Okay. So now we move to the next part, which from that example, the 3W frequency part, right? Okay. So now for this particular one, you clearly see that if you are trying to find the S component, that's the peak, right? The peak is 11.3578. We are looking for the S component, so cos, right? And the phase angle is what? 37. So 37.59, right? And that gives us 8.9999 dB, right? Now let's see what will determine whether here is plus or minus, right? Looking at this variable, if you have to draw that part as phasor, right, it will lead relative to the x-axis, it will lead, right? And if it is leading, meaning that the y component will be positive, which is the y component will be positive, so that side is a plus. You can clearly see from the phase angle whether it will tell you whether it's plus or minus, right? This is plus, right? Very clear that's a plus, right? And then you have our J, right? And the y side will be, so we just change it to sine, and then we have this, so that's 6.9283. So that's the whole I4 that we had in the example 2 in the rectangular or the Cartesian form, right? This is how it is, all this together, right? So if you have to do this in polar, it's very much straightforward. The polar, when you're transferring from this form to polar, is easier, right? So that's what we say. We say that the polar, if you need it in the polar form, right? All that you need is that you need a peak, right? The vector form, which is a vector, and then you need a phase shift, right? And then clearly this I4 has two parts, so I4, right? And what do we have? We have the first part, so let's see. Okay, so the first part, the maximum is that 19.9487, so straightforward. 19.9487, right? And what do we have? We just do this and then do it this way, and then write a phase angle, which is negative, right? So negative 10.662, yeah, so that's it. Negative 10.62. So that's how we write that first part in polar form, right? And then these forms are interchangeable. We can write from one form to the other. It's just a matter of representation of what is required. So let's see. Plus here. This sign here is very important. It shows whether it's leading or lagging. You can't skip these ones for the phase angle. So this is to be very important. Okay. So the next part will be where we have the 3W part, 3W frequency part, right? So let's see what we get for that. Basically straightforward as you've seen. So that's 11.3578. That's the peak. 11.3578. Appropriately, it should be something like showing that as a vector, right? Yeah, so that's the appropriate way. Most of the times you don't, the absolute this one is taken out, right? Just show that as a vector, right? Yes. So we have the peak value for the 3W parts. Then the phase angle. So let's see. The phase angle for that one is a plus. So plus, so you can just take it out of the back. Just to be safe, just make it plus so you see what's happening. And that's 37.59. Oh, sorry. 37.59 degrees. 37.59 degrees. Alright, so that's it. That's how we represent them in the rectangular Cartesian form and the polar form. So you clearly see that you can even convert from one to the other. So let's try for one. So we'll try for the first part. So let's see. So this one, for instance, right? So let's see. If we are trying to find the maximum, we just do square root of this squared plus this squared. Right. So now we are trying it for this side. Just this side. Just this, to see if we actually get what we had there, the peak. We get the maximum, we get the phase angle as well. Squared plus this squared, right? So the x is what? What do we have for the x? That's 19.6070, right? And then we have minus, right? Minus 3.6764, right? What do you have? That, so that's a 19.9486. That's 94, yeah. So that's very close to this, as we can see here, right? So when we are trying to get this angle here as well, we do the same thing, right? So we just do tan inverse the y. The y component is this. The minus here, very important. So minus 3.6764, right? And then we have 19.6070, right? Yeah, so you see clearly it gives us the, yeah, so 10 minus 10.62, right? So that's it. So we've tried it for that part. We will try for this. You can try if you want. And then we take it back. We are trying to use this one as well, right? For the polar, right? So if you are trying to convert from the polar to the original, or let's say from the polar to the rectangular, that's what we do. You just take the maximum, which is a 19.9487. If you want the x component, you do a cos, right? And you do minus 10.62, right? Yeah, so that gives you the s component, which is a 19 point dot, yeah, 90.6070. If you want the y component, right? If you want the y component, we clearly know that that's a sine. This is a minus here and c, right? So you see it gives us the s component, which is a minus 3.6764. Yeah, so that's it. Yeah, this is how we represent them, the Phasors in the rectangular Cartesian form, which is this right here, right? And in the polar form. And clearly you can see that what we've been saying so far is for each and every representation you need at least two things to represent them, and then they are interchangeable, right? But then one thing we'll be looking at here is that there's a way that we can use this polar or the rectangular Cartesian something forms when you are doing computations, right? And the calculator supports that. Unlike the what's the name? Unlike the time function one, the time domain ones, the representation can be punched directly in the calculator, or you can work within the calculator. But when it comes to the rectangular form, let's see. What you have to do is that you go to mode, right, and you go to complex, right, because you're representing them in complex forms. And then the Cartesian form, where is it? We clearly said that we have a s component, a g, and then a y component, right? Which is j could be I, right? So if you go to the complex, after you've gone to the complex mode, you press the mode, you go to complex, right? You press shift, you could see complex here, right? Just above the 2 digits, you press on it, and it gives you this option, right? You can see that the form that we are looking for here for the rectangular Cartesian form is this one, right? So you see rectangular form, as you can see here, the number 6. You tap on that, and then you can change whatever you have to that complex form, the rectangle or the Cartesian form, right? So this is what you have. So whenever you have values in this way, you can even add them or do computation with them, right? But when it comes to the polar form, the calculator supports it as well. So after you go to complex mode, shift, press 2, takes you here. You can see the complex form, right? Which is the r, this is theta here, right? So you see the r just here, the r, and there's the theta, right? Or the phase angle. The r is just telling you the peak value, which is basically the radius, right? Yeah. Yeah, so that's it. So that's a representation. Yeah. So you can interchange them. You can even use them when you're doing calculations and everything. The calculator supports that. All right.